Let's come back to the action. How does LA inhibit the conduction on the neuron? So we're gonna have a look now. Just now we have seen how it blocks from the perspective of pharmacology and also physiology. Now we're gonna have a look at from the perspective of chemistry. All right. If, as you know, if you just take example procaine in this case, LA, they are actually weak bases. So as a weak base, if you see this, we're coming to our favorite formula, where you have this base in the non-ionized form, when it actually can pick up as a weak base, it picked up a proton to form the ionized form of La. So it can actually exist in equilibrium. The non-ionized, the uncharged one, is more lipid soluble than the charged one, all right, which is more water soluble. These are some examples of local anesthetic. They usually comes in the form of amides and esters. So in terms of the clinical onset, so this is what you see. This is what manifested out there on patient. Clinical onset of all LA are not the same because they're based on a few factors. One of them again on the pKa. So how well it can pick up, and LA can pick up a proton, a hydrogen, and it is also due to the physicochemical properties of the LA, and also the ability of the individual LA to diffuse through the sheath or the membrane. As you see later, there are two modes. Remember, mode A and mode B. In mode B is whereby the LA will start to diffuse through the membrane, and the properties, the physical chemical properties of an LA will determine how well it can actually go through the membrane. In general, the closer the pKa of this LA to the physiological pH, the faster of the onset. Okay, with two exceptions: chloroprocaine and benzocaine, as you see later. So now let's dig deeper. Let's dig deeper from the chemistry point of view. Okay. So we're going back to mode B, because mode B, as you remember, is quite easy. It simply block the sodium channel, like tetrodotoxin. It's simply block on the extracellular level. La in the ionized form block. In mode A, it will actually block the sodium channel from the top, from outside. But now we're going to have a look at mode B, which is now it needs to go into 2 or 3 ways. Firstly, it's got to bind to the phospholipid, to the membrane, and then only then it can start to cross through the membrane, the lipid bilayer. Only then it can also help, in a sense, interfere with the conduction. Let's have a look closer. So when you have phospholipid, these are a structure of phospholipid. You have the phosphate here, and you also have at the end an amine. In this case, it's an ammonium, is positively charged amine. All right. In this case, what happens is that the in earlier one, let me show you. Normally, a lipid bilayer, it would have the phosphate will actually bind through ionic bond to a calcium. So La will displace the calcium, all right, in this case, and it will start to orientate itself, to the phospholipid. So then what you see here, firstly, there's a hydrophobic interaction, and then there's also this kind of ionic interaction between the positively charged amine and the carbonyl, because the carbonyl actually has a dipole moment, yeah. And there's a hydrophobic interaction as well between the the intermediate chain of this is in this case is procaine, and the phospholipid, and the other end of procaine is where you have this quaternary amino group, and that will interact through ionic bond to the phosphate. So when they displace, when La displaces the calcium, it will start to bind itself, it will start to reorientate itself with the phospholipid, all right, and therefore it will, in one sense, what happens is that it will also interfere with the conduction of the action potential across the membrane. Yeah? When that happens, it also helps to La to penetrate through the nerve membrane by crossing through the nerve, by crossing through the membrane. Yeah, as in the non-ionized form. Yeah. Right, let's go back to the schematic diagram. So once in a non-ionized form, it will penetrate through the first, it will start to bind and displace and penetrate through the lipid bilayer. Once it gets across the other side in intracellularly, what happens is that this non-ionized form will convert to BH plus, the ionized form, and then you'll start to block the sodium channel. There's a typo, there's no plus here, it should be Na channel. You'll start to block the sodium channel from the inside. Research have shown that there's a particular binding site on the sodium channel in the inside part of the an axon, yeah, that will help La to bind to the sodium channel. So what happens here? What happens in between? Yeah, from this non-ionized form to ionized form. Yeah. So remember that an La is a weak base. So, and it usually exists in equilibrium depending on the pKa and pH of the pH of the area around here. Yeah. So the if you see here as well, once this non-ionized form of the La goes across the membrane, you will then start to pick up hydrogen in here, and it can actually form the ionized form of the La. Alright, so that's about it. Remember, there's two modes of action in for an La. From the chemistry perspective, the first mode is whereby the ionized form will block sodium channel extracellularly, like tetrodotoxin. The second mode is mode B, whereby the non-ionized form will have to first bind and displace the calcium. All right, you have to know how they actually bind. Make sure you know them structurally as well, and then they have to go across. Only then can go across and start to pick up a proton, then transform into an ionized form that will then bind and block, bind to the sodium channel and block the incoming sodium from entering into the intracellular space, and that actually sort of stop or block the conduction or propagation of the action potential.